vector of the xy coordinate plane pointing in the direction within that plane I should be walking when I raise up to the surface at that particular point right here, so that I get the direction of gradient descent. That's why it has to be a sequence. All right, I think this model is -2, -1. You guys, I'm nervous. I don't know if I answered the question.
What was it?
Yeah, I did. It was merely finding the gradient of f at that point.
Well, part B is what I had trouble with.
Yeah, that's what I haven't read yet. So part B, if you don't have your book, you guys, the author's asking, the author's stating, let C prime be the path of steepest descent on the surface, beginning at the point P, and let C be the projection of C prime onto the xy coordinate plane. Find an equation of C in the xy coordinate plane. So here's my x-axis. Here's my y-axis. Here's my z-axis, and I think the curve in green, I said curve, sorry, I think the surface in green looks something like this. Can you guys appreciate how I'm not unitizing my axes? I'm not being that careful. But if I allow C prime, oh my goodness, you're right, that was the word, wasn't it? Thank you. I agree completely. I did look back. But again, I'm being a little sloppy, guys. I'm not unitizing anything. So, let's come back. C prime is the path of steepest descent on the surface, beginning at P. So, let me go to the point 1, 1, 1. Let me talk about that curve C prime, which, by the way, with my red pen, looks something like this. Well, my vector was -2, -4, so probably something like this. Now, if I look at the projection of that path C prime, hold on, you guys, I'm a little slow because I don't remember the rest. If I look at the projection of C prime onto the xy coordinate plane, so this is called C prime, that curve, I think the projection is going to be nothing more than a line. Looks like that. The author's labeling that C.
And it's projecting on the what again? Sorry?
I'm projecting C prime onto the xy coordinate plane.
Oh.
Then.
Okay. So
Yeah.
it's dot product? Projecting onto dot product?
Oh, I won't even go that far. By the way, I think I made another crude mistake today. I really did. It's probably going to be the case this line happens to pass through the origin. I think what I drew in the board was too sloppy. And keep in mind, everybody, when you look at the blue line that I have on the board, that's supposed to be lying in the xy coordinate plane. So in the xy coordinate plane, hold on, I still need to read. What number is this?
So that's C prime onto the xy coordinate plane?
Yes, so C, which is what I should have labeled in blue, is nothing more than the projection of C prime onto the xy coordinate plane.
And why do you say it probably goes to the origin?
Excuse me.
Why do you say it probably goes to the origin?
I was looking over here. Or how about saying this? No matter where you are on a paraboloid, but not at the vertex, don't you agree that probably the direction of greatest descent is going to be going straight towards the vertex?
Yeah.
I'm cheating. I've got a lot of pictures in my head. So is everybody okay with my picture? Keep in mind what you see in blue is not in 3 space floating around somewhere, it's just in the xy coordinate plane.
Wait, so is it going through the origin or is it going through that point?
It's going through the origin.
Both.
It's not going through the point 1, 1, 1 because that's not in the xy coordinate plane. I want you guys to attack me on this because I want you to understand my picture since I'm usage and not a job drawing.
It's been sort of a related thing. How are C and the gradient vector different? Are they pretty much the same?
Well, when I'm talking about C, I'm talking about a whole line. To me, the gradient vector is just a directed line segment. But you're right. In a sense, they're synonymous because, have you taken Math 33? Because technically speaking, that ray, that gradient vector, is generating every point of the line.
C prime is the steepest ascent?
No, C prime is the curve passing through that point 1, 1, 1, where I am traveling in the direction of steepest ascent.
Well then,
Well, he said
I guess
descent,
what
same
I'm wondering is why doesn't it the line pass through the same points where the red hits the xy plane?
Oh, they do. You just can't see it in my picture. They pass through. They intersect.
On the other side.
They do.
Okay, that's why I was.
But you're right, they do.
Okay, I
And they
understand.
probably both zero, y equals 0, with different z values, of course, at that time.
Then I agree. I agree.
Right, so C and C prime make kind of like a plane of kind of like slicing a span.
Yeah.
Yeah, you can do it that way. Think of C prime as being the curve of intersection between a vertical plane that's on top of the gradient vector and the surface itself. You can interpret it that way.
So the base of the object is, right now, or how you drew it, is below the xy plane?
The base of what object?
There, that curve, the oval.
Well, no, that's just
Oh.
the extent of the draw.
I see. I just meant that the parabola goes downward. And
Okay.
when I draw the oval, I'm not saying it stops there, I'm just saying it goes on
But,
indefinitely.
right, okay, okay.
And if you know, you got a good point. Like I said before, it's a lousy way maybe of presenting the surface in 3D space, but what else can I do? I mean, I suppose I can do this in a goofy fashion. It just looks awkward to me.
It looks like a jellyfish.
I didn't.
Actually, I should be complimented.
Okay, so the blue line is flat on the XY plane.
Yes, it is, but the red curve C prime is
So
not.
are we looking straight down then?
No.
Well, I hate to say straight down because most of the surface is below the XY coordinate plane we're looking up.
Okay, but
That's
this is
why-
where, if we were, the line would be blocking our view of the C curve then.
Yeah.
Yes, it would, or how about saying this?
Yeah.
Walking along that blue line, looking up or looking down, straight up or straight down, you're looking at the corresponding points on C prime, which is in
All right.
red.
Don't leave this below it.
All right, so what was the question on B to answer?
I don't know, I'm sorry.
Now that we've thoroughly
I was just
analyzed
trying.
the shape.
Well, I want you to, because I want you to understand the image. Find an equation of C in the XY coordinate plane? No, that can't be the question.
Well, all we've got to do is find the projection of C prime onto that plane.
And it's
So
the same
equals to
zero.
This is a really simple math D question, isn't it?
Couldn't we just take these off?
Well, look at that gradient vector. I'm running out of colors. In black,
That is the slope, right?
well, in black, isn't that the gradient vector?
Wait a minute.
Oh, yeah.
It
Oh,
is.
sorry, I put it in the wrong position. Hold it. Project this point straight down. I guess it's this vector.
But that vector is, of course, pointing towards the direction of ascent. So if we wanted something that pointed toward descent, we just flip the signs, right?
True. Is that what he wanted, by the way?
I mean,
Which one was
matches the
it?
line.
Was it ascent or descent?
Descent.
Which
Descent.
one?
Decent.
Which one?
Doesn't matter.
And it's 100% irrelevant because they're going to lie on the same line. But you're right. I did misspeak. He wants to line in the direction of greatest descent. I said ascent, but who cares? It's the same line. So let's just do it. Oh, yikes. Somebody give me this point over here.
I have a quick question.
Yes.
So that's the gradient vector
Yes,
that
it is.
shows that shows the greatest descent whatever the guy wants. And you put it right there at the edge of the call it paraboloid bowl, upside down bowl.
No, don't look at it. Has nothing to do with it. I was simply taking the point P, projecting straight to the XY coordinate plane,
Okay.
and looking that direction. It had nothing to do with a dotted green thing I had in the back.
Okay.
So let's compute the location of the terminal point. It's located at,
1, 1.
Wait, I'm confused because why would it have an endpoint if it's a vector that we're trying to find? Are we trying to find a vector or a...
well, there is a vector. I've got it right here. Mitch.
But isn't it asking for a line?
What is it asking for again? Sorry?
The equation of the line you see in blue.
Okay, so why do we need endpoints for it if it's a line?
Thank you. I think I'm wasting my time. I think all I need is the point I've already given, which is 1, 1, 0. There's nothing wrong with what I said. It'll work. Just why go through all the work? So what's the slope of this line that you see in blue? 2.
0. It's just stays.
I'll wait for the right answer. It's a math E question. 2, 1. I agree. What's the y-intercept? 0. We use 0, 0.
0.
So what's the equation?
Oh, shoot.
Thanks.
Why is it not 2? Why is the slope not 2?
Well, because when I move in the x direction 1 unit and the y direction 1 unit, the rise over run is 1
So
unit.
it's
why
not,
does it
it's
pass
not
through
the
the
gradient
origin?
vector?
You guys, my apologies.
That's it.
I do have the wrong value. That's the gradient vector. I do take that back.
Okay.
My apologies.
That makes everything make sense now.
Does it pass through the origin still? That's why I'm confused.
Now I'm confused.
Well, this line must pass through the origin because it's on the xy plane and it's traveling in the
No.
direction of greatest descent. The direction of greatest descent will pass through x equals 0, y.
In my head, I just did the image in my head. I thought it passed through the origin, doesn't it?
But it has to pass through 1, 1, and it has to be along that vector.
C prime passes through 0, 0, 4. Then the projection of C prime on the xy plane will pass
You know
through
what, you
0,
guys,
0.
I made a mistake, and here's my mistake.
Over there.
What I said was correct. Stanhope's paraboloid, excuse me. The direction of great ascent will necessarily pass through the vertex if it's a circular paraboloid. Am I graphing a circular one? And this one's not circular. Thank goodness, because I think my answer was so simplistic, but I made that mistake. So can I take it back? Yes or no? Is this a point on the blue line? And I think because the direction is not going straight towards the origin, this time the line does not pass through the origin because it's not a circular paraboloid, but a non-circular elliptical paraboloid. Ouch. So you know what? I do have to take care of the endpoint. I guess it's not that quick of a math D question. Well, pretty quick, but not as quick as I suggested.
So
Where's the terminal point?
Why do you need an endpoint?
Well, I'm trying to find the equation of the line.
Don't you have a
Don't I
slope?
typically write an equation of the line this one?
But don't you have a point and a slope already?
What's that?
Don't you have a point and a slope already?
Yeah, I could do that as well. I'm just saying, typically when I create an equation line, I like to write down the points of the formula. Maddie, I'll do it your way in a minute, and we'll see if they match up. I got a point on the line. It's just 1, 1. Ah, shoot, you guys, I goofed up. I don't have a slope, so I'll take a break. And I'll simply compute the slope by looking at the ratio of rise to run, y2 minus y1 over x2 minus x1. You guys, seriously, this is a math D quiz, isn't it? And, oh shoot, I need a second point on the line. Piece of cake.
Just take that point P, but
Just take -2, subtract it from this x coordinate, what do you get?
you get -1. Or no, you get 3, sorry. X coordinate is subtract -2 is 3.
-3.
Oh, so you're going the other direction. So you're getting positive 3, 5. You could have gone the other direction as I was suggesting. Doesn't make any difference. Now that I got 2 points on the line, life's a piece of cake. I think I have, is that a 5 minus 1 over 3 minus 1?
Equals 2.
I'll put everything in. And I've got that my y minus 1 is equal to 2 times x minus 1. I'll clean up and put it in a pretty form.
So Matt was right, it was a slope of 2.
Yes, it is, I agree. Is that, I can't do my arithmetic. Is that minus 1?
Wait, no,
Minus 2.
Minus 2, distributive.
Oh, because then you add the 1. Never mind.
Yeah, you just tell me if I made a mistake. And Maddie, you were just me doing this. You're saying, well, let's consider the equation already in slope-intercept form.
Yeah.
We know what the slope
No.
is.
I was saying the slope is just rise over run, -4 over -2, which is.
And so you put in the slope right away.
Oh, okay, yeah, I guess
And I
that's.
just like this technique in math D because now I gotta solve the equation for B, which you could. We'll get to
Well,
see.
no, I did it there and I just put n in that one and
Oh,
used
I
one.
see. So you were okay with my point slope form, which is
Yeah.
how I computed the slope.
Yeah, it was
I agree.
hard.
Hard.
Well, and it's.
So, I had a question about a non-circular paraboloid. So we can say for a circular paraboloid, the direction of greatest ascent or descent is going to be towards the vertex.
Yeah, when I first drew the picture, I wasn't even recognizing that I did not have a circular paraboloid.
Is there a named point on an elliptical paraboloid toward which the direction of greatest ascent is, or
Can you say that again? I'm sorry.
is there any specific known point, like a focus or whatever, that would be a similar thing on an elliptical paraboloid where we know that all the directions of greatest descent will go toward? Is there some known point, like one of the foci or something that we know that going towards it will give us the direction of greatest descent?
Not that I can think of. It's gonna depend on what point I'm on in terms of that surface, which is a little bit different.
Okay.
Way back in the beginning, you said the vertex is where?
Well, don't you agree the vertex of paraboloid is necessarily 0, 0, 4? Do you see it?
Yeah, I was thinking that the difference between the coefficient for the x and the y made a difference, but that's just elliptical.
Completely relevant. That just simply tells me how elongated I am in one
Okay.
direction as opposed to another in the xy coordinate.
Now, if it was x minus something squared or y plus something squared, that would change the vertex, right?
Yes.
What do you mean? Oh, yes. You're saying this. If the output of my function were like this, where's the vertex?
1, -3, 4.
+1, -3, 1,
that skill is still.
So that's what I got. In the back of the book, it says y equals x squared.
Holy moly.
Why is it squared? 4x is greater than or equal to 1.
Holy.
If someone wants to double check me, I feel like I've looked at it 5 times.
But this is the equation of a line, not the equation of a.
Well, let me read it again, maybe I misread it. Let C prime be the path of steepest descent on the surface, got it drawn. Beginning at point P, we've got that. And let C, without the prime, be the projection of C prime on the xy plane.
Oh, it's gonna curve.
Yeah, because it doesn't go through the vertex.
It's not completely vertical.
Right. Well, I don't see it. I mean. Oh.
Mr. Pelkey, what if the intersection's like this?
What intersection?
C prime, what if it's like this, and then so when you put it straight down, it becomes a curve?
It certainly could be the case, but
Well, because the direction of greatest descent may not necessarily be just a vertical slice
Yeah, it might not be
of
like
that
this.
parabola. It could be more of a curved thing.
No, an angle.
How come you use this? How can you use the slope formula, not just getting it from the? This is a little off topic, but
That's what I
not
said.
just getting it from the vector. Did you just use the vector?
yeah, we did it both ways. Yeah, we did it both ways.
So instead of like this, it's more like this.
You're using pronouns this, what does this refer to?
Or like,
Do you want to go through like draw?
flat is, well, it's easier to do with my hand anyway. Flat is the XY coordinate plane, and when you draw the thing on the
C prime.
on the curve, when you draw C prime on the curve, it ends up being not like this, but like
Maybe I would draw it.
Wait, I only know what
like this.
So,
you
It's not gonna do it.
so
What is
No, like the slice like
Yeah, I
this.
see. Like you call it this thing.
Right.
If you were to
Yeah.
look at this,
I see what you're saying. So the
'Cause so when you
projection
look
is
straight
curved
down.
then.
if you were looking straight down,
Like
those
this.
gives you parabolas of function.
straight down looks
Not like this.
But what if this was skewed at an angle so that it's
That'd be way more complicated.
sorry about the red, but if this was skewed more,
See this curve?
and then
I
the
see
projection
what
on the
you're saying.
and then the projection on the xy plane looks more like this for this C
And
prime.
then it drops straight down.
What?
So you're saying a projection could be curved in the xy coordinate, I agree completely. But in this example, I should be a line.
Well,
Why?
maybe did we make a mistake in looking at what our direction of greatest descent or descent is?
No,
for-
that's just perfect.
The book's known to have typos in it too.
Wow.
That's possible.
You guys, I just don't see it, I'm sorry.
Yeah.
I just don't see it. Now, I could have made a more complicated surface where we do have that projection of C prime onto the xy coordinate plane, certainly could be a curve, but with this elliptical parabola. And besides that, I think the gradient vector would have nonlinear components.
And it has that exact gradient vector right next to y equals x squared.
So I'm sorry,
It's weird.
I don't know where they are.
Maybe somebody was like drinking too many bottles of beer when they were writing that textbook.
So
or something.
the
Well,
gradient vector.
typically an author will not write his own solutions. They hire cheap labor for that, called graduate students.
So maybe the graduate student was out at a frat party the night before and
So
Oh, trust me, grad students in mathematics typically do that.
is it aligned because the gradient vector is pointed like
It's
in
linear.
terms of z, it's straight up?
In terms
Or
of Z,
in
it's
terms of
straight
z,
up.
it's just like going, it's not angled at all. Is that why?
Well, I think because the gradient vector, no matter where I'm in points, is moving in a linear fashion. Out of C squaring.
Do you want to see the solution manual?
Do you have it?
Yeah.
she is equipped.
I'm actually trying to.
I just don't understand why the fact that the xy is linear has anything to do with
Yeah. I mean,
how.
it's because if you were to stretch that out more, the direction of greatest descent might angle more.
The direction of greatest descent is always given by that equation,
Yeah, so it changes.
but it's always linear. You can't put an extra y in there to make it a curve.
Oh, maybe you could. I don't know. Maybe we missed something in the original function. Maybe there was like a little superscript or something that we missed.
Hold on a second. What do we get? I don't see it. Well, it's the same thing.
Yeah. That bugs me.
What?
Sorry, I don't know if you guys studied this back in Math 31, separable differential equations.
If we studied it, I'd probably suppress the memories.
Don't be like that. I'll take another look at it later. But when I solve my DE, I'm getting this. You guys, I don't have much to say today. I've got a pretty short topic. So, sorry, another opportunity for you guys to look at my lousy drawing. I have a surface free space. This time, if you guys don't mind, I'm not going to draw my coordinate axis system. But at a specific point, I might want to talk about the corresponding tangent plane to my surface. And relative to what you guys know about tangent lines back in Math 30, this should be fairly straightforward. I think the tangent plane and the surface are not the same. In at least the way I drew my picture, it appears that the tangent plane only touches the surface at a single point, but later on, further away from the point, I don't care if it crosses. And I think, locally speaking, if I were to dive in and zoom in and blow up my picture, I think the distinction between the tangent plane and the surface are going to be closely the same. The further and further I zoom in, the closer and closer that approximation is for the tangent plane relative to the surface.
So it's like a derivative kind of thing?
Very much like that, yes. And if you guys don't mind, I'd like to talk about the equation of a tangent plane.
What section is this?
I have no idea. 12.7. Guys, I feel kind of guilty in class. I feel like I've talked about these completely separate notions, little topics here, little topics there. I finally next week when we come to class, we'll at least be able to do something kind of meaty, which is optimizing, which is what you guys did last semester. Sorry, I misspoke. 2 semesters ago.
Math 30.
We're just going to be optimizing the free space. We're going to be taking surfaces like this and trying to find those points that give you local max and local mins. So we'll get it. Just give me one more day of some small tidbits.
Does related rates return
Of course.
When?
in this class?
When?
I don't know.
In about 20 minutes.
In 20 minutes? Oh, awesome.
So everybody, I've got a surface. It's going to be described by this equation. Well, not that one, but maybe Z can equal that decimal. Oh, you guys, I don't like it. Can I bring everything to one side?
It's still
Sorry. I really don't like it. Don't listen to me. You guys, can I rewrite it this way?
Z minus f of x, y equals... Yeah, I guess you can. It's ugly, but you can write it that way.
But you know what's nice about writing it this way is I can think of this as the output of a function in 3 variables.
Oh, so
Huh?
a function within a function, kind of?
In a sense, you can think of it that way. And let's see if you and I can't find the equation's tangent plane by taking a peek at that point. I'll call it P. Actually, in addition to that, do you guys think with my green pen, I can talk about a curve past that point that's actually on the surface?
On the tangent plane or on the surface?
On the surface. So that green curve is on the surface, not the tangent plane. And let's suppose the green equation can be mathematically modeled by something like an R bar of t. So R bar of t is simply a vector that's got an x component, a y component, and a z component.
Very complicated x, y, and z components, probably.
Well, potentially, yes, potentially. And I think if I were to partially differentiate f, that big F, you guys are big sloppy again, that's the big F, not the small f. If I were to partially differentiate big F with respect to, I don't know, what do you guys think, x, y, or z?
Just start with x, maybe z.
Yeah, how about going deeper than that? Because I think when it comes to the function big F, it's broken up into 3 components, x, y, and z. It's just x, y, and z themselves can be interpreted as functions of t, particularly when I look at the vector value representation of that curve on the surface. So let's partially differentiate with respect to t.
That looks a lot like our general.
Very much. It's just that when I partially differentiate, oh, actually, I can take this one step further. I've just got one independent variable. You guys take care of it for me. What do we got?
Hold on a second.
I'm just using a chain rule. partial of big F with respect to
X, dx,
derivative
dx dt.
of x. Got it. You're on a roll.
Plus
Partial
partial
f
f with respect to y times dx dy dt.
Same for Z.
Partial f with respect to z. Big long
Oh shoot. This looks familiar. This sort of looks like the dot product between this vector. And this one. Oh, but shoot. This looks like the gradient for big F. Dotted with, isn't that just simply R bar prime T? You guys attack me if you see something online.
Looks like a pretty good derivation to me.
I was gonna ask one thing, sorry. For Z, why is it that we can say it's a function of T and not a function of X and Y? Like,
Oh, I can. No, what you're saying is fine. You can think of Z as a function of X and Y just like I did. And that would describe the surface. It's just that when it comes to like that green curve, which is not the whole surface, just a green curve, I think it's convenient to describe that in terms of some kind of parametric representation.
So
That's all I'm suggesting.
So this is the gradient of f dotted with the velocity of t.
If you want to interpret it that way, you can. I'd interpret this as the second factor's velocity, if it's the case the original function represents position. And I just wasn't even going that far. I was just looking at it as a direction vector myself.
Okay.
But you guys, take a peek at this R bar prime T. I think I can take a look at this projection in the xy coordinate plane. I can look at an arbitrary value of x in the xy coordinate plane, come back up to this particular point P from there, and refer to this point P as having coordinates, I don't know, how about x naught? Y naught and z naught? And I can literally interpret that direction as nothing more than the result of this vector.
What direction?
What are we equating to right now?
I'm just trying to describe this particular thing as a vector. And I'm just describing it as a pointed line segment.
Wait a minute, I'm not sure if I like that.
Why?
This one here is a derivative. This here just looks like a modified line of position vector. I'm not exactly sure to see how that equates.
Well, all I'm suggesting is that this itself is a vector.
Okay.
And I simply look in the xy coordinate plane, looking at the vector, then going back up to the surface. It's just a direction vector. Regardless of whether it's derivative or otherwise, it's just a direction vector. And I think if I actually take a peek at this dot product, expand back out, even though it looks like I'm going backwards, I think what I'm really left with when I look at that dot product is simply the partial f with respect to x at that point times my x minus x naught plus the partial, oh everybody, another mistake, that's a big F, not a little f. I'm getting too sloppy again. Plus my big F with respect to y, evaluated at this particular point, times y minus y naught. Oh, I'm running out of room. One more term. Plus the partial of big F with respect to z, evaluated here, times z minus z naught.
That looks a lot like the equation of the kind that we got in 12.1.
Exactly. I just had A's, B's, and C's instead of the partials with the big F. And so it really does mimic exactly what you and I had in the past. So if I gave you a surface described as such, this is exactly how you can come up with the equation, how you can come up with the equation of a tangent plane. Now personally, I think typically you're going to be looking at equations of tangent planes given that the surface is described in this fashion. So don't take this the wrong way. What I have on the board in this big red box is indeed a standard form for the equation of the tangent plane. At that point, x naught, y naught.
One heck of a big standard form.
If you don't like it, I'll change it. And if you don't like it, take a peek at this representation of the big F. Is everything above my brace? If you were to partially differentiate this with respect to x, what would you get?
Did you say tangent unit plane?
I hope I didn't. It's just a tangent plane at the X naught, Y naught, and Z naught.
So, partial, that F sub X, that notation means just that again over on the blackboard, right?
Yeah, and you notice how I keep interchanging notation? I think they're synonymous. I sometimes use this notation for the partial of big F spec X, but sometimes I use a subscript instead.
And then the X naught, Y naught, Z naught is together.
Well, yeah, because I'm taking it
Yeah,
to the
okay.
partial big F at that particular point in sequence. Caleb?
So you said projection over there, is that R or R prime?
It was the R bar.
Okay.
Would you guys agree with this? That if I treat what's above this brace as an alternative name for big F, isn't the partial of big F with respect to X just simply the partial of little f with respect to X?
Pretty much.
With a negative sign out front? Evaluated merely on the point X naught comma Y naught times my X minus X naught. Plus, I will now partially differentiate this version of big F with respect to Y, but the Z goes to 0. And I'm merely left with a partial of little f with respect to Y. Evaluate on this 2-coordinate point. Oh, sorry, did I forget my negative sign? Times my X minus Y naught. Plus the partial, now let's be careful, plus the partial of this big F with respect to Z. But the partial with respect to Z is going to be what?
That's supposed to be Y minus Y naught.
Yes, it is. My apologies. Jeepers. So you guys help me with this. What is the partial of that big F with respect to Z when you look at big F in the form of Z minus F of X comma 1?
When did you get the derivative of Z?
Which is 1. I agree. Oh, you know what? I don't like this. You guys are getting stuck. I want to talk about just two variables, X and Y. I don't want to put my Z naught in there. So can I just change it? If X and Y are replaced with X sub naught and Y sub naught, doesn't Z just become F evaluated there for that particular choice of Z? If you don't mind, I'll write it as such. F evaluated X sub naught comma Y sub naught. Oh shoot, I don't like this. I didn't make any mistakes. I just think it looks sloppy. So let me rewrite this equation in a more alternative standard form. I think it looks like this. Partial of F spec X at A comma B times X minus A plus the partial of F spec Y at A comma B times X minus 1. And then plus my F of AB. This is going to give me the corresponding Z values on the equation, excuse me, on the tangent plane of the curve.
So it's
X minus Y.
X minus Y. What is?
Oh, sorry.
Y minus
My
B.
apologies.
Yeah.
Y minus.
Y minus B.
You guys, I think I just said something wrong. I said the equation of tangent plane to the curve. I meant this is the equation of tangent plane to the surface, not the curve. And I might have just wasted 5 minutes of your time. I know we already have a means by which we can compute the equation of tangent plane. That required a normal vector. And instead of using a normal vector, I'm using the gradient vector, which makes a lot of sense. Because a gradient vector has to be going in the direction of the greatest descent from one level surface to another for the function big F in higher dimensional space. Somebody had a question I talked over. Matt?
Just notation again. So when it's sub X or sub Y, what's the difference between sub nothing over there? Yeah.
That's the original function describing the surface, because the surface is described as Z being equal to F of X comma Y. So in other words, Maddie, no derivatives. It's direct evaluation.
Oh, so if there's a sub, it's automatic derivative?
Well, yes, I defined this notation right here as being a shorthand for this notation.
I just, yeah.
They're synonymous. And if you think it's grammatically confusing with the subscript notation, just don't use it. Use the other notation if you prefer. Oh, you guys, we are, when did class start? So we're 45 minutes in class. Can I start my first example?
I thought you were writing about the exam.
Yeah, when you wrote exam and stopped, I'm like, oh, we just
Sorry,
had
that was
one. There's a heart attack here. I'm like, somebody get me the defibrillator.
Just get this back.
Yeah.
We're gonna need to do a bit of self-revival here.
Surprise! I didn't teach you that with you.
Somebody play Mozart's Requiem for my GPA.
You guys, nothing unique about this example. I'm making it up out of thin air. I do some arithmetic.
Then of negative line.
I think you just took that equation from the.
What's that?
And then change the 4 to a 3.
Are you serious?
Yeah.
All right, we'll change it.
Oh. Oh, no, I just wrote it in pen.
How's that? No, seriously, I don't want to mimic the book. The book's got an example like that.
Well, that was just the one we did for that.
We just did it,
Question.
right?
Oh, the last question. Well, that was okay. All right, now I got to think again. If x is 1, y is 2, would z be 6, I think?
What does that say?
Is that the same point I have to
Wait,
grab?
wait. You had to negative
Oh,
6.
it's negative.
Oh, okay, so that's pure coincidence. So you guys, it's this easy. Here's my standard form for the equation. Z equals the partial of f, evaluated here, times x minus a, plus the partial of f with respect to y times y minus b, plus my f evaluated there. And I think in this particular example,
Wait, is there supposed to be FY AD?
thank you. I don't have to put it,
You don't have to put it?
because I evaluated the partial at that point, but just to be clear to the reader, I'm putting it in. But if you didn't put it in, that's fine. As long as you evaluate the partial at that point. Oh, by the way, I didn't compute the partials, did I? So I think the partial of z with respect to x is, you guys talk. But the partial of z with respect to y is, so x plus 2y, I agree. Oh, let's compute. It's just easy. Look at the partial of f with respect to x, evaluated with 1, 2. Jeepers, does it give me 2?
Is that t, partial t with respect to x?
Well, these are all partials of z, because I'm looking at
Oh,
this.
that's a z.
And I got my a value being positive 1. Plus, you guys, you do the work. What's the partial of f with respect to y evaluated at point 1, 2? 5. That's what I got. Times y minus. Oh, shoot. How did I come up with this number?
You already have it.
Yeah, I already have it. I just have to listen to 6. If I'm making you nervous, give up. Come back to the equation for big N for the left. Subpointed for x, 2 and for y, you still get a 6. To be honest with you, in my head, that's why I generated a 6 arithmetically speaking anyways, but I made up the example. Oh, shoot, you guys, I'm done. There's the equation I'm playing. Or if you prefer,
So this is the equation of the tangent plane.
it's the equation of the tangent plane to my surface at the point 1, 2.6.
Can there ever be more than one?
No.
Okay.
If there's more than one tangent plane, that means you didn't have continuity with either one.
But what if you have, oh, I see. I mean, if you have a curve that's,
Why don't you do something simple?
Okay.
Consider the cylinder. That means like this at a little angle.
right,
You could think of 2 tangent planes here, but technically speaking, there is no tangent plane because I don't have differentiability there on that entire line.
so is it always on the concavity on the tangent planes on the outside? I mean, because you could have a,
Not necessarily